In addition to finding volumes using double integrals, I can also, surprisingly, find areas using double integrals as well. At times, we can encounter regions that are more complicated than those we've worked with so far, and we might have to consider breaking these regions up into smaller regions that are each easier to work with. When we do this, we call it decomposition. And this process gives us a sum of separate integrals, each with its own limits of integration. A common example of where this happens is when the bounding functions for my region change at some point in the general region I'm working with. It's extremely important, as always, to make sure that we accurately identify the limits of integration for each of my subregions when I have to do this. So when I decompose these regions, I take the entire double integral over the entire region, f of x dA, and I break it up into subregions. And I can have 1, 2, 3, all the way up to n regions, depending on how complex the region is I'm working with. I might have a double integral over R1 plus a double integral over R2 plus a double integral over R3, all the way up to a double integral over Rn. Double integrals can also be used to find areas in cases where my integrand is the function f of xy is equal to 1. Since volume is area times height, I get a double integral over region R of f of x dA is equal to the double integral over R of 1 dA, which is equal to A. In other words, as long as my function is equal to 1, this integration process will give me an area. So let's let R be a region in the xy plane. Then the area of R will be given by the double integral over the region R of dA. Let's work an example. I want to use a double integral to compute the area of the following region. I'm going to make a sketch of the region as well so that I can visualize what I'm talking about. The region that I'm talking about is bounded by the parabola y is equal to x squared and the line y is equal to x plus 2. I'm going to sketch the region first because it helps me to understand whether or not I have to break this region up into subregions. In this case, you'll notice that my straight line x plus 2 intersects an upward opening parabola at the point -1, 1 and at the point 2, 4. I'm okay computing this area with a single double integral. There's no place in this region where I'm going to have to change my limits of integration because of the way the region is defined. So I'm going to take the integral from -1 to 2 of the integral from x squared to x plus 2 of 1 dy dx. I do the inside integration first, and I get the integral from -1 to 2 of y evaluated from x squared to x plus 2 dx. This gives me an integral from -1 to 2 of x plus 2 minus x squared dx. This becomes x squared over 2 plus 2x minus x cubed over 3 evaluated from -1 to 2. I plug in those limits of integration and I get 9/2 for the area bounded by these two curves. Here's another example. I'm looking for the area of the region in the first quadrant that is bounded by the parabola y is equal to x squared, the line y is equal to 5x plus 6, and the line y is equal to 6 minus x. I need an idea of what this region looks like, so I'm going to graph this region first. The region sits between the line y is equal to 5x plus 6 and the line y is equal to x squared, but it also lies above the line y is equal to 6 minus x. I notice that when x lies between 0 and 2, the subregion is bounded on the top by 5x plus 6 and on the bottom by 6 minus x. And then in the region from 2 to 6, the subregion is bounded on the top by 5x plus 6 and on the bottom by x squared. This means I'm going to have to break up my integral into two subregions. The subregions will be computing the area in the region from x is equal to 0 to x is equal to 2, and then compute the area from x equal 2 to x equals 6, and then I'll add them together. So that my area is the double integral from 0 to 2 of the integral from 6 minus x to 5x plus 6 of 1 dy dx plus the integral from 2 to 6 of the integral from x squared to 5x plus 6 of 1 dy dx. This gives me an integral from 0 to 2 of y evaluated from 6 minus x to 5x plus 6 dx, plus the integral from 2 to 6 of y evaluated from x squared to 5x plus 6 dx. This gives me the integral from 0 to 2 of 6x dx, plus the integral from 2 to 6 of the quantity 6 plus 5x minus x squared dx. This gives me 12 plus 54 minus 58 thirds, or an area of 140 thirds square units. Now you get to try it. Pause the video and find the area of the region bounded by the curves y is equal to 1 plus sine x and y is equal to 1 minus sine x on the closed interval from 0 to pi. When you're ready, restart the video to check your understanding. The first thing I want to do is graph the region so that I can visually determine whether or not I need to break this up into subregions. When I graph the region of the two curves between 0 and pi, I get a curve bounded on the top by 1 plus sine x and on the bottom by 1 minus sine x, and the two curves intersect at the endpoints of my interval. This means I don't have to break my area up into subregions. I simply have to compute the area is equal to the integral from 0 to pi of the integral from 1 minus sine x to 1 plus sine x of 1 dy dx. This gives me the integral from 0 to pi of y evaluated from 1 minus sine x to 1 plus sine x dx. My integral becomes the integral from 0 to pi of 1 plus sine x minus the quantity 1 minus sine x dx. This simplifies to the integral from 0 to pi of 2 sine x dx. I get negative 2 cosine x evaluated from 0 to pi, which gives me an area of 4. So this is how I can use double integrals to compute an area. Keep in mind, you may have to break your region up into subregions depending on how your region is bounded by your functions. Be sure and let me know if you have any questions.